Machine learning, ML, is a branch of artificial intelligence, AI, that focuses on building systems capable of learning from data, identifying patterns, and making decisions with minimal human intervention. It has transformed numerous industries, offering innovative solutions and enhancing efficiency. This extensive overview aims to elucidate the concept, types, methodologies, applications, and challenges of machine learning. Introduction to machine learning. Machine learning is the science of getting computers to act without being explicitly programmed. In essence, it involves the use of algorithms that can learn from and make predictions or decisions based on data. Arthur Samuel, a pioneer in this field, defined it as the field of study that gives computers the ability to learn without being explicitly programmed. Core concepts. Data. The foundation of machine learning is data. This data can be structured, like databases, or unstructured, like text and images. The quality and quantity of data significantly affect the performance of ML models. Algorithms. These are the mathematical constructs that make sense of the data. They can be broadly categorized into supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Model. A model is the output of a machine learning algorithm that has been trained on data. This model can make predictions or decisions without being explicitly programmed to perform the task. Training. This is the process of feeding data to an algorithm to help it learn. The algorithm adjusts its parameters to minimize errors in its predictions. Testing. After training, the model is tested on new data to evaluate its performance and ensure it can generalize well to unseen data. Types of machine learning. Supervised learning. In supervised learning, the algorithm is trained on a labeled dataset, meaning that each training example is paired with an output label. The goal is to learn a mapping from inputs to outputs. Classification. The output variable is a category. Examples include spam detection in emails, sentiment analysis, and image classification. Regression. The output variable is a real value. Examples include predicting house prices, stock prices, and temperature forecasting. Unsupervised learning. Unsupervised learning deals with unlabeled data. The system tries to learn the underlying structure from the input data without any output labels. Clustering. Grouping data into clusters of similar items. Examples include customer segmentation, document clustering, and image segmentation. Association. Finding rules that describe large portions of the data. Examples include market basket analysis and recommendation systems. Semi-supervised learning. This is a middle ground between supervised and unsupervised learning. It uses a small amount of labeled data and a large amount of unlabeled data. This approach can significantly improve learning accuracy when acquiring a fully labeled dataset is expensive or impractical. Reinforcement learning. Reinforcement learning involves training an agent to make a sequence of decisions by rewarding it for good decisions and penalizing it for bad ones. This type of learning is inspired by behavioral psychology and is used in areas such as robotics, game playing, and navigation systems. Key algorithms. Linear regression. Used for regression tasks, it models the relationship between a dependent variable and one or more independent variables. Logistic regression. Used for classification problems, it models the probability of a binary outcome. Decision trees. Used for both classification and regression, decision trees split the data into branches to make predictions. Support vector machines, SVM effective for classification tasks. SVM finds the hyperplane that best separates the classes in the feature space. K-nearest neighbors. K-in a simple, instance-based learning method used for both classification and regression tasks. Neural networks. Inspired by the human brain, these are used for complex tasks such as image and speech recognition. Deep learning, a subset of ML, involves neural networks with many layers, deep neural networks. Random forests, an ensemble method that uses multiple decision trees to improve the robustness and accuracy of the model. K-means clustering, a popular unsupervised learning algorithm used for clustering tasks. Model training and evaluation. Training process. Data pre-processing, cleaning and preparing the data, including handling missing values, normalizing features, and splitting the data into training and testing sets. Feature engineering. Selecting and transforming variables to improve the model's performance. Model selection. Choosing the appropriate algorithm based on the problem and data characteristics. Training. Feeding the data to the algorithm to learn the parameters of the model. Evaluation metrics. Accuracy. the ratio of correctly predicted instances to the total instances. Precision, the ratio of true positive predictions to the total predicted positives. Recall, the ratio of true positive predictions to the total actual positives. F1 score, the harmonic mean of precision and recall. Mean absolute error, MA, the average of the absolute errors between predicted and actual values. Mean squared error, MSE, the average of the squared errors between predicted and actual values. Applications of machine learning. Machine learning has penetrated various fields, significantly transforming them. Healthcare. Disease diagnosis. ML models can predict diseases such as cancer from imaging data. Personalized medicine. Tailoring treatments based on individual patient data. Predictive analytics. Forecasting patient outcomes and hospital readmissions. Finance. Fraud detection. Identifying fraudulent transactions. Algorithmic trading. Using ML models to make trading decisions. Credit scoring. Assessing the creditworthiness of individuals. Retail. Recommendation systems. Suggesting products to customers based on their past behavior. Inventory management. Predicting demand and optimizing stock levels. Customer segmentation. Grouping customers based on their purchasing behavior. Transportation. Autonomous vehicles. Self-driving cars use ML to perceive their environment and make driving decisions. Route optimization. Finding the most efficient routes for delivery and transportation. Predictive maintenance. Anticipating vehicle breakdowns before they occur. Natural language processing, NLP. Speech recognition. Converting spoken language into text. Machine translation. Translating text from one language to another. Sentiment analysis. Determining the sentiment expressed in text. Challenges in machine learning. Despite its potential, machine learning faces several challenges. Data quality and quantity. High quality, large datasets are essential for training accurate models. Issues like missing data, noisy data, and biased data can significantly impact model performance. Model interpretability. Many ML models, especially complex ones like deep neural networks, are often seen as black boxes. Understanding how they make decisions is crucial for trust and regulatory compliance. Overfitting and underfitting. Overfitting. When a model learns the training data too well, including its noise and outliers, it performs poorly on new, unseen data. Underfitting. When a model is too simple to capture the underlying structure of the data, leading to poor performance even on training data. Computational resources. Training large models, particularly deep learning models, requires significant computational power and time. This can be a barrier for many organizations. Ethical concerns. Bias and fairness. ML models can perpetuate and even amplify existing biases in data, leading to unfair treatment of certain groups. Privacy. Using personal data for training ML models raises privacy concerns. Job displacement. Automation through ML can lead to job losses in certain sectors. Future directions. The field of machine learning is rapidly evolving, with several promising directions. Explainable AI, XAI. Developing methods to make ML models more interpretable and transparent is a growing area of research. This includes techniques to explain how models make decisions and to ensure they are fair and unbiased. Federated learning. Federated learning involves training models across decentralized devices or servers while keeping data localized. This approach enhances privacy and security, as data never leaves its source. AutoML. Automated machine learning, AutoML, aims to automate the end-to-end process of applying machine learning to real-world problems. This includes tasks like data pre-processing, feature engineering, model selection, and hyperparameter tuning. Integration with other technologies. Combining ML with other technologies like the Internet of Things, IoT, blockchain, and quantum computing can lead to new applications and enhanced capabilities. Conclusion. Machine learning is a transformative technology with the potential to revolutionize various aspects of our lives. By enabling systems to learn from data and make intelligent decisions, it opens up numerous possibilities across different sectors. However, it also presents challenges that need to be addressed, including data quality, model interpretability, and ethical concerns. As research and development continue, we can expect even more innovative applications and solutions to emerge, further integrating machine learning into the fabric of modern society.